Good morning to all. We'll start with module 6, which deals with distributed shared memory. So, in distributed shared memory, we'll be discussing about what is meant by distributed shared memory, what is the importance of the concept of shared memory in a distributed system. And to implement this distributed shared memory, we should have consistency models, and we'll be seeing about some case studies which is relevant to page-based distributed shared memory and shared variable distributed shared memory. So, we all have learnt about what is the importance of memory in a single process system. So, we are using in our day-to-day life a single process system. Memory is very, very important, wherein you store all the files, all your data in the memory, and you have an appropriate retrieval process for retrieving your data. So the data which you have it in your memory is updated, and you have the recent copy of the data, because there's only one user who will be updating your data. So there is no inconsistency problem which is associated with the memory in a normal single process system. But when it comes to distributed system, maintaining a single copy of the data is very difficult, because in a distributed system you'll be having multiple users. Any user can share any data, can use any data, and if a write is being done by one user, it has to be visible or it has to be updated to all the other users also. So this is relative to consistency memory coherence problem, which we have studied in the earlier modules. So the concept of distributed shared memory is the heart of the system of distributed computing system, and this was being proposed in the early 90s. So distributed system is nothing but it is a collection of workstations, and all the machines have been connected via the LAN. So the idea here is to have that each and every machine will have some memory, and you call that memory to be a single page to memory, right? So if suppose we have 100 machines, each and every machine will have one page of memory, and all the 100 pages now contribute to a virtual address space. Okay, so we have 100 user, 100 computers or 100 machines. Each and every machine will have a single page of memory, and a distributed system can connect all the single pages together and totally can call it to be a virtual address space. So one page is present exactly on one machine. So whenever I refer to a data which is present on my own memory, you call it to be a local page reference. Okay. So if suppose I want to access a particular file, that particular file, if it is present in my own memory, I can directly refer to the system memory and you can take the page. So this can be done at the highest memory speed because it is local to your machine. If suppose I want to refer or take a data from a memory which is being with some other remote machine, what we do? So usually the request is being passed to the operating system, and the operating system in turn connects to the OS of the remote machine, and your data will be taken. So whenever you want to refer to a page on a different machine, we trap to the operating system the request is being transferred to the remote machine. From the remote machine, the data is being taken and it is being given to the client. So the operating system will send a message to a remote machine, and you find the page and it is being sent to the requesting processor. So here distributed system is nothing but a collection of workstations or machines connected by a local area network, and every computer or every machine will have a single page of memory. A client can access either the memory within his own memory, which you call it to be a local page, or he can access a memory which is present in a remote machine memory, which is being done with the help of the operating system. So you trap to the OS, connect to the remote machine, take that particular page, and then send it to the requesting process.
மேம் சில பேர் லாக் ரூம்ல வெயிட்டிங் ரூம்ல வெயிட் பண்ணிட்டு இருக்காங்களா? கொஞ்சம் அலோவ் பண்ணிட்டீங்களா மேம்?
எஸ் மேம். பரத். ஓகே மேம். ஒருத்தர் தான் இருக்கோம், பரத் மட்டும்தான். So, as far as the user is being concerned, the user thinks like it is like a multi-process system, and you're able to read and write any data into the shared memory as well. So whenever you access the shared memory, there is a communication between the systems and you should have synchronization. These are not visible to the user at all. It will be done at the system side. So we should develop, there should be a software which will maintain all the communication between the processors and also all the synchronization between the data. So this system is very easy to build, and but it has a very poor performance because you transfer the pages, right? You have to move the pages from one machine via the LAN to the requesting process. So the pages are to be transferred back and forth across the network, hence there is a huge network traffic. So programming is easy in this particular model, but there's a performance bottleneck because every time there is a when there is a remote access, you take the page from that machine, transfer it to your own client machine and start working with it. So the pages are being transferred back and forth across the network, and this it will increase the network traffic, which will gradually minimize the performance of your distributed shared memory. So the idea of designing a distributed shared memory should be to minimize the network traffic and to also reduce the time delay which is involved in making a request and getting a reply. So if suppose I make a request, it will take me about 15 to 20 minutes for getting my file. Then the user will not be satisfied with that and the work is not completed. So usually the distributed shared memory should be designed in such a way that the amount of network traffic, the amount of transferring the pages should be minimum, and also the time delay which is incurred between requesting a page and getting that page should also be minimum. So there are different types of distributed shared memory systems available, and shared memory can be controlled either through hardware or through software. So here we see three different types of distributed shared memory, which has to maintain consistency. Everything totally dependent only on the software. There is no hardware in dependency on this. So three types of distributed shared memory where you can maintain the consistency completely through software. So these three are called page-based distributed shared memory, shared variable distributed shared memory, and object-based distributed shared memory. So the examples are given. IVY is one system which is a page-based DSM, and Moonin, there's one more system called Medway which is called shared variable DSM, and Linda is one system which goes into the third topic, which is object-based distributed shared memory. So the basic idea of sharing of shared memory is that multiple clients has to access the data. Every client can access the data either with his own machine or he can get the page from the remote machine, with the idea that the time delay should be very minimum and the network traffic also should be minimized. So whenever there is a sharing in the memory, the data which you have in the memory should be consistent. So so maintaining consistency will be easy if suppose we have only one write page and read page can be multiple pages. So anyone can read, whereas you can perform a write operation with only one particular copy of the page. So that is an easy method of implementation, but this is very difficult because the network traffic will be more since you have only one page of writable. If suppose we have multiple clients which wants to do a write operation, again you have to wait, and the page has to be transferred between the client and to the remote machine, and this will take a huge amount of network traffic. So having only one writable page and multiple read pages is an easy method of implementation, but it has performance bottleneck because we have to share the pages again via the network. So what shall we do? We shall allow multiple copies, right? So every writable, you can allow multiple writable pages, but when you allow multiple writable pages, you should have all the copies to be consistent. So all the pages should have the same data. The data should not be different in the same file, right? So if suppose I replicate the file f1 across 100 users, all the 100 users should have the same data. The data should not be different. So when you have multiple copies, then it is easy for the implementation of distributed shared memory. But keeping all the copies to be the same or consistent is difficult. So what people have done is they have designed models which is called consistency model. So consistency model is nothing but it is a contract between the software and the memory which will maintain the consistency even if the page is shared among multiple users. So consistency model is a contract between the software and the memory. So whenever the software is being given certain rules and regulations, if suppose this software follows the rules, then the memory will work correctly. If suppose the software violates the rules which are given in the consistency model, then the memory operation will not be consistent. So you may have different data in the across the users for the same file. So consistency model is nothing but it is a software which will tell you the contract between the software and the memory, and if this software follows up with the rules of the consistency model, then the memory will work correctly, consistency is implemented. Otherwise, consistency is not guaranteed. So there are a variety of rules. So having from strict rules, you can slowly deviate the rules, and there are many types of models which comes under this consistency. So there are a wide range of contracts starting from major restrictions to minor restrictions. And as you know, the major restrictions models are difficult to implement, but it is more consistent. And the minor restrictions model may be easy to implement, and it has some issues. So you have a wide variety of contracts, and which will finally give you different types of consistency model. So we have a variety of consistency model in DSM. So this is a very, very important topic of study, and you surely have a detailed question on this. So there are various consistency models. We'll be seeing about the first two in this class, and the remaining we'll see in the next class. So there you have different models like strict consistency, which imposes major restrictions or stringent conditions or strict rules into the consistency model. The next one is slightly lenient than that, which is called sequential consistency. The third one is the causal consistency, pram consistency, weak and release consistency. So out of the six model, the first one imposes strict or stringent conditions on the model, and release consistency is it is a very lenient model which imposes minimal restrictions. So we'll see what the strict consistency is. So strict consistency is a model which has a very strict rules, and here we explain the consistency model with the help of the processor. So here processes are defined by P1, P2, P3, etc. And this is a line which will tell you the timing, right? So you start from 0 millisecond, you go to 10 milliseconds. So this will tell you, the straight line or the horizontal line will tell you the order of the timing, and W of x represents a write operation and R of x represents a read operation. Okay. So as per this example is concerned, we have two process P1 and P2, and we have a write operation W x of 1. So which means perform a write operation to a memory location x. The value which is written is 1. So W x1 is nothing but perform a write. W represents a write operation. X represents the memory in which the memory location in which you do a write operation, and 1 represents the value which you have written. Similarly, Rx of 1 is nothing but a read operation, read from the memory location X, and the value that is read is 1. So here you explain the consistency model with the help of this diagram. So we have multiple processes P1, P2, P3, P4, and it is being shown at different heights. So P1 is here and P2 is lower than this. If you have the next process, I can have P3, P4, etc. So the process are being depicted in different heights, and the operations which are done by the process is shown horizontally. So this is the straight line will separate the process, and it represents the time. So this starts from 0, 1, 2, 3, 4, 5, etc. So this is an increase in the time operation. So wx of a that we have explained, x w is the write operation, x is the memory location, and this is the data value which is written. So the condition for strict consistency, or the rule which governs the strict consistency model, is that whenever we read any data from a memory location, it has to return the value which is being done by the most recent write operation. So if suppose I read a data from a memory location X, it has to provide me with the latest or the recent data which has been written. It should not give me any old data, right? So this is the rule with respect to strict consistency model. Okay. Whenever you do any read operation, whenever you read a data from a particular memory location, it has to give you the value which is being done by the most recent write operation. So initially you assume all the values of the variables to be 0. So we have two models here. In the first model, what we have done, we have done a write operation to a variable x with the value 1. So after some time, the process P2 reads the data from the memory location X. The data which it gets is 1. So you get the most recent value here. Hence, this model follows the strict consistency. So whatever value is being recently written into the memory is being retrieved by the read process. Hence, we say that this model is a strict consistency model. It follows the rules of that. Whereas when you come to the second one, here the process P1 does a write operation on X with a value of 1. But after some time, process P2 is reading the value of X, it gets a value 0. So this is not a consistent model. There is a value 1, 1 da and the X la irukku. But when you read from P2, it retrieves the value of 0. So this is not a strict consistency model. So the read should get the most recent data which is being written. Go through this. So the first one is a strict consistency model, and the second one is not, because the value 1 is present in X, but when you read, it retrieves a value of 0. So it is not a strict consistency model. Okay. So P2 does a read after the write, but it gets a 0. Hence, it is not a strict consistency model. For the second subsequent read, it gives 1. Anyway, it has not read the recent value. So strict consistency is very difficult to implement, and it is almost impossible to implement. And in strict consistency model, one thing which you have to keep in mind is that global time ordering is maintained, right? So this is the global time ordering. All the process will follow the same timing. Okay, so it will follow the same time. So global time ordering has to be maintained. So time increases from left to right. So when the memory is strictly consistent, all the writes are visible to all the processes, and all the process should stick on to the same time, which we call it to be global time ordering. And if suppose a memory location is changed, so if suppose I change the value of the memory, all the reads have to get only the new value. So that is a strict consistency model. The second one is sequential consistency. So sequential consistency is a slightly weaker model than the strict consistency model. And here there is one concept wherein it permits memory interleaving. So memory interleaving is that all the process will see the same memory references, but valid interleaving is acceptable, right? So a memory in which one process sees one interleaving and another process sees another different one is not a sequentially consistent memory. And in sequential consistency, there is no reference to time at all. So you don't have a global time ordering, and there is no reference to the recent data which has been read or written. So in sequential consistency, when multiple processes run in parallel on different machine, interleaving is acceptable, but all the process should see the same sequence of the memory references. So here there is no global timing as been given in the strict consistency model. So nothing is said about time, and there is no reference to the recent value. So here again, both are sequentially consistent, right? So here there is no global ordering of time and no timing based data is given. So a value of x is x1 is being written to x, and p2 reads the value of x, it reads the value of 0, which means there is an interleaving and it may have read the previous value. But again, when P2 reads, it sees a value of 1, which was just written. So this is a sequentially consistent model. So there is an interleaving here wherein X might have read the value previously, and after the second time execution, it might read a value of 1. So this is right. So the timing here, P2 follows one timing and P1 follows some other timing. Here the second one, P1 and P2, it may follow the same timing, and the reads here will retrieve the value of 1. This is also correct. So this is called a sequentially consistent memory wherein interleaving is allowed here. So sequentially consistent memory does not guarantee that whenever you do a read operation, it will return you the most recent value. So it guarantees that all the process see the memory references in the same order. Okay, that's what this has been sequentially consistent. So all the process will see all the memory references in the same order. And sequentially consistent is programmer friendly. It's easy for the programmer to do it, but it is very expensive and the results are also not deterministic. So that's up with the sequential consistency. So I think we'll stop with this for today and we'll continue the remaining in the next class. So we have seen consistency models is very, very important. So we have seen about two models here, strict and sequentially consistent. Strict consistency is a read operation will return you with the most recent write, and global time ordering is there. Whereas in sequential consistent, interleaving is allowed and there is no global time ordering, and every process may have its own time clocks, its own time it may have. So one condition here is that all the process should see the all the process should see the same memory references in the same order. So that's with sequential consistency. So both these are sequentially consistent. Okay, students, we'll stop with this for today.